Hey guys, today we're going to be going over section 8.2.1 in your textbook, so make sure you have those out and return to the correct section. We are skipping over right now 8.1.5. We'll go over that on our dot day together. This one, which is a little bit easier to do as a pre-recorded lesson, so that's kind of what I wanted to do with you guys. So today we're going to be talking about similar figures. So we've learned about similar figures in the past. We know that similar figures have the same shape but not necessarily the same size. We know that their side lengths are proportional, and we call the proportion of their side lengths the zoom factor. So kind of we'll be using all that today to help us compare the areas of similar figures. So we're going to go ahead and kick it off on question 867. And as we kind of work through this together, please make sure that you're writing in your textbook or on a separate sheet of paper, that you're taking notes, that you're trying the problems. If I ask you to try something or think about something, make sure you do that. If I ask you to pause the video and try a problem, make sure you do that, okay? That's going to be vital in you kind of in this learning process, making sure that you're actually learning and not simply watching a video. All right, so to start this question out, it says, to celebrate the victory of your school's championship girls ice hockey team, the student body has decided to hang a giant flag with your school's mascot on the gym wall. To help design the flag, your friend Archie created a scale version of the flag measuring 1 foot by 1.5 feet tall. So there's some important information. We've got a scale drawing of the flag that we want to make. The student body thinks that the final flag should be 3 feet tall. How wide would this enlarged flag be? Okay, so we need to figure out how much it grew. So it was originally 1.5 feet tall. We have our new version is 3 feet tall. So if I want to figure out how much bigger it got, I can do 3 divided by the original size, 1.5. So I can see that the height grew by 2. So if the height grew by 2, then the width needs to grow the same amount. So the original width was 1 foot. So our new width would have to be 2 times 1 foot, which is 2 feet. Because if the height grows at a certain rate, then the width needs to grow at that same rate. Okay, so remember that's called the zoom factor. The zoom factor for these would be 2. All right, let's look at part B. If Archie used $2 worth of cloth to create his scale model, then how much will the cloth cost for the full-size flag? So again, we're remembering that the height and the width of the new flag is 2 times as big. So I want you to think about, if the original was $2, how much should I charge for the new flag? So go ahead and think about that. I want you to come up with your own answer. I'm not gonna do it my own guess. I'm gonna let you kind of keep your guess in your head, and we're gonna just remember what your number is, write it down on part B, and we're gonna look at part C in that. So part C, you're supposed to have like this little piece of paper that you cut out some triangles and blah blah blah. Obviously we can't do any of that with you guys being at home, but what we're gonna do to kind of help us think about part B, how much we should charge for our new flag, or how much it would cost to make our new flag. We want to think about how many of the original flag or the scale versions would fit within the new one. So I want to think about how many of these small flags would fit in here. Would 2 fit in here? Would 3 fit in here? Would 4 fit in here? And so on. So I want to figure out how many of those will fit, because I know that each one is $2. And so if I can figure out how many of those go into it, then I can multiply that number by 2 to figure out what that new version is going to cost. So I've went ahead and kind of showed you this. So here was our original. It was 1 foot, and I have fit those original ones into this new 2 foot flag. So remember, we had a factor. We're using a factor of 2 here. Okay, that was our zoom factor. The side lengths were 2 times as big. But look how many of our original flags fit within this new flag. It wasn't simply 2, it was 4. So if I count them up, we fit 4 flags in here. Now if each flag cost $2 and there are 4 of them, what should be the cost of my new flag? So the cost of my new flag should be 4 times 2, or $8. Okay, so was your guess correct? Okay, did it grow the way that you thought it would grow? Okay, so think about that a little bit. So we're going to go ahead and answer that here. Our cost, it fit 4 of the flags. So the cost should equal $8. Okay, so it grew by 4 times, not 2. Our zoom factor was 2, but the area grew by 4 times as much. All right, let's look at part D. So part D says the student body is reconsidering the size of the flag. It's now considering enlarging the flag so it's 3 or 4 times the width of Archie's model. How much would the cost for a similar flag that is 3 times as wide as Archie's model? So we need to figure out what our new cost would be if the flag is, instead of being 2 times as big, is 3 times as big. Okay, so I need to consider how many of the original scale versions would fit within our new version that's 3 times as big. So I've went ahead and created one for this as well. This one's not quite as neat, but you'll get the kind of general idea. So there was our original flag, and I've put that original flag within the 3-foot version. Yes, it's upside down. And we just want to count up how many that was. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. So I can see I can fit 9 of the original flags into that new one that's 3 times as big. So the factor, again, the original factor, the side lengths were 3 times bigger, but we fit 9 triangles within that. So if I take 9 and I multiply it by the cost of each one, I'm going to get the cost of my new flag, which would be $18. Okay, so we can see here we could fit 9 flags. So the cost of the 3 times as big one would be 18. Okay, so notice again the zoom factor was 3 and it fit 9 flags. The zoom factor up here was 2. It fit 4 flags. So I want you to think about that pattern. I'm not going to show you the one that's 4 times as big. I want us to just think about it. So if the factor is 4, I want us to consider how many flags would fit within that shape. So again, just to reiterate, when the factor was 2, 4 flags fit. When the factor was 3, 9 flags fit. So when the factor is 4, then 4 squared flags would fit, or 16. So if you notice, the ratio of the areas is going to be whatever the factor is squared. If the factor was 4, 16 flags fit. If the factor was 5, 25 flags fit. Okay? So if I wanted to calculate the cost of a model that's 4 times as big, then I would do 16 times the cost of one of those flags, which is $2. So that would be $32. All right, so let's go ahead and see if we can read the next problem and kind of go through that. Okay, so question 68. It says, write down any observations or patterns you found while working on the problem 867. Okay, so we've already kind of seen that when our factor was 2, the areas grew by 4. When the factor was 3, the areas grew by 9. Should have used a capital A here. And when the factor was 4, the area grew by 16. So if our factor was R, what would our areas grow by? They would grow by R squared. Okay, so if we know the factor, if we know the comparison of the sides, we can square that to get the comparison of the areas. So it says, for example, if the area of one shape is 100 times larger than the area of a similar shape, then what is the ratio of the sides? So we know that the ratio of the areas, it gave us that in the problem, that's 100. So if we wanted to find the ratio of the sides, we want to think about how to do that. Okay, the area is 100 times bigger, so we want to figure out how much bigger are the side lengths. So we're going from R squared, the ratio of the areas, to R. So how do we get rid of a squared? Well, we square root it. So we know the ratio of the sides would be the square root of 100, or 10. So I could say the side lengths are 10 times larger in my new shape than my similar one. Okay. All right. So now we're going on into question 69. There are 4 different parts to this question. I would like you to try these on your own and then kind of come back and watch the video and see how many of them you got right. So if you'll go ahead and pause the video now, try A, B, C, and D, and then come back and check your answers to those, okay? Okay, so here's the solution to part A and B. So the first thing I did in part A is I saw that the scale factor was 5. So I knew that the areas had to be growing by 5 squared, or 25. So if the area of the smaller figure was 17, then I needed to multiply that by 25 to get the area of the larger figure. So then the area of the larger figure must be 425 millimeters squared. Okay, so we're not multiplying by 5 because 5 is comparing the side lengths. That's why it uses that word linear. Okay, it's just comparing the sides. So we have to square that in order to compare the area. All right, so let's look at part B. It says what is the scale factor and then what is the area of the smaller. So it gave us 2 side lengths, so we can find the scale factor pretty easily by just comparing side lengths. So that would be 4 to 10, or 40 to 10, which is 4. And then it asked us to find the area of the smaller one. So since the scale factor is 4, I know that the area of the larger figure is 16 times as big as the area of the original, 4 squared. So if I know the area of the larger figure, then I can divide that by 16 to get the area of the larger figure, which must be 41 units squared. All right, so now I want you to pause the video again, and I want you to try part C and D. Okay, so in part C, simply you were asked to find the scale factor and the ratio of the areas. So to find scale factor, I compared side lengths. So I saw that in the smaller rectangle, the height was 2. In the bigger rectangle, the height was 3. So I could say that the scale factor is 2 to 3, or if you said 3 to 2, that's fine too. And then it asked me to compare the areas. So to find the areas, I simply counted up how many squares each rectangle was made of. So I could see that the smaller rectangle was made up of 4 squares. If I count all the squares in the larger rectangle, it's 9. So then the ratio of the areas would be 4 to 9, or 9 to 4, depending on what order you went. What I did want you to notice here is that if you take the scale factor and square it, you should get the ratio of the area. So we would have 2 squared over 3 squared, which equals 4 over 9. So you can count all the squares individually to find the area. You can also know that the ratio of the areas is just the scale factor squared, and that would work too. In part D, it gave you the dimensions of 2 rugs. So it said, hey, they ordered this one rug. It was 16 by 24. They realized it wasn't the right size, and they needed one that was 8 by 12. The cost of the 16 by 24 was $800. So then the salesperson saying, okay, I'll charge you $400 for the 8 by 12. And it was asking kind of, is that a fair price? Well, no, because think about it. They're going to calculate cost based on the area, on how much carpet was used, right? So even though the side lengths are 2 times as big, or half as big, the area would be 1/4 as big as the original area. So then the cost should be 1/4 as big as well. So if the cost was $800, the new cost should be 1/4 of that, which is $200, not $400. So he is overcharging for that rug. Okay, the last thing I wanted us to look at was this problem, 870. Now we don't know how to do every single part of 870. That's what we're going to be learning on our dot day. But I just wanted us to kind of go ahead and start thinking about it so that on our dot day we can come back and kind of revisit this problem and complete it. All right, so it says if the side length of a hexagon triples, okay, so go ahead and think about what that's telling you. How does the area increase? Okay, and that's the only part of this problem we're going to do for now. So, for example, the original side length of the regular hexagon was 10. Now it's 30, so it tripled. It increased by 3. How would the area increase? So if our scale factor is 3, what is the ratio of the area? Because that'll tell us how much the area should grow. So go ahead, pause, answer that question real quick. When you unpause it, I'll give you the solution. Okay, so hopefully you got that the ratio of the areas would be 9. Because if I take my scale factor and I square it, I get the ratio of the areas. All right, so that's it for today. Make sure you complete your assignment. If you have any questions as you're working on it, please feel free to reach out to me and let me know. Remember, we do have a Zoom session on Monday and Thursday. If you need additional help with anything, use those time frames for that. On our dot day, we will be kind of diving into the next lesson because we have a limited amount of time and we'll probably have a lot that we'll want to accomplish. Bye, guys.